Let's start this section and this part with a reminder of what it means to be a factor. The number 6 has factors 1, 2, 3, and 6 because 1 can be multiplied by something to get 6. 2 can be multiplied by something to get 6, and so on. That's what makes 1, 2, 3, and 6 factors of 6. What those things are changes with each factor. The thing I have to multiply by 1 by to get 6 is 6. I have to multiply 2 by 3 to get 6. 3 needs to be multiplied by 2, and 6 needs to be multiplied by 1 to get 6. Notice that if 1 is a factor, then 6 must also be a factor, because 1 and 6 are the things that you have to multiply by each other to get 6. Equally, if 2 is a factor, and 3 is the thing I need to multiply by 2 to get 6, that automatically means that 3 is a factor. Here's a different number, 15. What are the factors of 15? 1 times something is 15. 2 times something won't give me 15. Well, actually it does, but it's 2 times 7.5. And we're only interested in integers. We're only interested in whole numbers here. So I won't count 2 as a factor of 15 because the thing I have to multiply it by isn't a whole number. The next whole number that I can multiply another whole number by to get 15 is 3. The next one is 5. The next one is all the way up at 15. So the factors of 15 are 1, 3, 5, and 15. So that's what it means to be a factor. What about a common factor? Well, notice that 6 and 15 have a factor in common. All this really means is that 3 goes into 6 and 3 also goes into 15. Notice that 15 goes into 15 and 5 goes into 15, but 5 doesn't go into 6. So each of these numbers has a group of factors, but they only have one common factor, and that's 3. Let's compare these two numbers. What factors do they have in common? It may be difficult to tell at this point, but we have a technique for determining what all the prime factors of a number are. Let's start with that. I can write 27 as 3 times 3 times 3. But I can also write 27 as 1 times 27. I could also write it as 3 times 9, or 9 times 3. So this process, making a factor tree, helps me write 27 as the product of all its primes. But it's not the only way to write 27. The factors of 27 are any of the numbers that appear as a part of one of the ways to write 27. So I have a 1, I have a 3, I have a 9, and I have a 27. The factors of 27 are 1, 3, 9, and 27. Let's do the same for 36. 36 can be written as 2 times 2 times 3 times 3. But to write it as the product of two factors, I can write it as 2 times 18, or I can write it as 4 times 9. I can write it as 12 times 3, or I can write it as 6 times 6. I can also write it as 1 times 36. You can always write any number as 1 times itself. So the factors of 36 are 1 and 36, 2 and 18, 3 and 12, 4 and 9. Generally, if we're just asked for a list of factors, we'll make that list with commas between the numbers. Are there any other factors of 36? Have we missed any? Well, we have 1, 2, 3, and 4. Do 5, 6, 7, or 8 go into 36? 5 doesn't. It doesn't end in a 5 or a 0. But 6 does. I left that out. 6 is a factor. 7 doesn't go into 36. 8 doesn't. 9's already in the list. 10 and 11 don't. 12's already here. What about 13, 14, 15, 16, or 17? I can check each one and I'll find out that none of those goes in either. In fact, here's a shortcut to making sure you've got all the numbers. Here's a shortcut to making sure you've got all the numbers that are factors of 36, or of any number. Figure out what the halfway point of your list is here. I have 1, 2, 3, 4, 5, counting the 6, 6, 7, 8, 9 numbers in my list. The 6 would be the halfway mark. In other words, I have 4 numbers in each half of my list, and the 6 is right in the middle. Since 1 and 36 are both factors because 1 times 36 equals 36, and 2 times 18 equals 36, means 2 and 18 are both factors, and so on. 3 times 12, 4 times 9. So if 1, 2, 3, and 4 are factors, 36, 18, 12, and 9 automatically have to be factors. Once I figured out that the only number missing from the middle of the list was 6, and notice that 6 appears twice, 6 times 6 is what gives me 36. Once I'd figured that out, I didn't really need to check the back half of the list, because each of the numbers in this half has to have a partner in this half. Okay, so now we know what the factors of 27 and 36 are. What about common factors? Well, they both have 1 as a factor, they each have 3 as a factor, and they each have 9 as a factor. So the common factors of both of these numbers are 1, 3, and 9. Those are the factors that are common to both of these numbers. So what's the greatest common factor? Well, that's just the biggest one. The greatest common factor of 27 and 36 is 9. 9 goes into both of these numbers, and it's the biggest number that does. So it's the greatest common factor. Make a quick mental note now that how we've been talking about factors is as the two things multiplied together that give you 27, or two things multiplied together that give you 36. We're going to need that idea in the next screen. All right, let's find the factors of 6x squared and 15x. Then let's find any common factors. And finally, we'll find the greatest common factor of both of these things. Remember that factors just mean two things that are multiplied by each other to give you the big piece. So one of the things I can do with each one of these is separate it into two parts. 6 is a factor, and x squared is a factor. Here, 15 is a factor, and x is a factor. But each of these breaks down even more. 6 has the factors 1, 2, 3, and 6. I can write x squared as 1 times x squared, or as x times x. But that's it. Those are the only two ways to write x squared, as a product of two things. So, what are the factors of x squared? Well, they're all here. 1, x, x again, but I'm just making a list of factors, so I don't need to write it again, and x squared. These are the factors of x squared. Let's go over here. What factors make up 15? Another way to think of this is, what goes evenly into 15? Well, 1 certainly does. And remember I said they needed pairs? If 1 goes in, then how many times does it go in? It goes in 15 times. 1 times 15 is one way to write 15. What's another way? 3 times 5. 3 goes in, and it goes in 5 times. So automatically we get the idea that 5 goes in, and it goes in 3 times. These two are kind of partners. Here's my list of factors of 15. What about my list of factors of x? Well, the only way to write x as a product of two things is 1 times x. So 1 and x are the only factors of x. So what are the common factors of 6x squared and 15x? What do they have in common? They each have a 1, they each have a 3, and they each have an x. I'm looking for common factors. I could say that this was common as well, but I've already got a copy of 1 in my list of common factors. The common factors of these two things are 1, 3, and x. Okay, this is where it gets a little bit more interesting. I'm trying to build up 6x squared by multiplying two things together. I can multiply 1 by 6 to get 6, and I can multiply 1 by x squared to get x squared. But I'm not trying to build them up separately. I'm trying to find a way to write 6x squared as the product of two things. So really, I have to think about this more as being put back together again. In other words, I can write 6x squared as 1 times 6x squared, or 2 times 3x squared, or 3 times 2x squared, or 6 times 1x squared. And that's not it either. I could also write 6x squared as x times 6x, 2x times 3x, 3x times 2x, or 6x times 1x. In this list down here, I don't have any duplicates. 1 times 6x squared is different from 6 times 1x squared. In this list, or group, I do have some duplicates. X times 6x is the same as 6x times x by the commutative property of multiplication. And 2x times 3x is the same as 3x times 2x by the commutative property of multiplication. So while here I've got a nice list of the factors of 6, and here I've got a list of the factors of x squared, when I'm working with more than just a number, I have to look for all the different possible ways that I might be able to write 6x squared in this case as a product of two things. It's more than just breaking down the number separately from the variable. Let's go do this over here. How can I write 15x? Well, I could write it as 1 times 15x, or 3 times 5x, or 5 times 3x, or 15 times 1x. Can I write it any other ways? I can't. The reason I could do this one more ways was that I had an x squared, and so I could write x squared as either 1 times x squared or x times x. So this list is all the ways I could write 6x squared as a product of two things where one of those things included an x squared. And this list came from all the ways that I could write 6x squared as a product of two things where each of the two things had an x, where the x times x gave me the x squared. Here I don't have an x squared, so this is my complete list of all the ways that I can write 15x as the product of two things. There are 4 things in this list. So now I can take a more accurate look at what the common factors are. What's in this list that's also in this list? Well, this tells me all the different ways I can write 6x squared, but it doesn't tell me what the factors are. Same thing here. The factors of 6x squared are the things that I used in making up 6x squared as a product of two things. X is one of the things I used to make 6x squared. What I had to multiply it by was 6x. So x is a factor and 6x is a factor. I also used 2x times 3x to get 6x squared. So 2x and 3x are also factors of 6x squared. I used 1 and I used 6x squared. I used 2 and 3x squared. I used 3 and 2x squared. And I used 6 and I used x squared. What did I use to make 15x? I used 1 and 15x. I used 3 and 5x. I used 5 and 3x, 15, and just x. Here are all the factors of 15x, and here are all the factors of 6x squared. Where are the common factors? They both have a 1 in the list. They each have a 3. There are no 5s here, and there are no 2s here. But there is a 3x in this list, and a 3x here. No 6s down here, and no 15s here. What about x? X is in both lists. Have I missed anything? There's no 2 down here. There's no 5 up here. And there are no x squareds down here at all. So the common factors are 1, 3, x, 3x. 3x also goes into both 6x squared and 15x. Not only that, but 3x is the biggest of all the common factors of 6x squared and 15x. So 3x is the greatest common factor of 6x squared and 15x. The way in which we're actually going to be using this idea going forward is that if I give you a binomial or something longer, and I ask you to find the greatest common factor of this binomial, you're going to look at the individual terms, the 6x squared and the 15x. And you're going to tell me that since 3 and x both go into 6x squared and 15x, that I can write 6x squared plus 15x as a multiple of 3x. I'm kind of doing an undistribution thing here. I'm first finding what was distributed to make this, and then figuring out what it was distributed against. So here I have 3x times something equals 6x squared. What do I need to multiply by 3x to get 6x squared? 2x. And what did I need to multiply by 3x to get 15x? 5. We can check it simply by doing the distribution. 3x times 2x is indeed 6x squared. And 3x times 5 is indeed 15x. There's a little bit of vocabulary you need to know about here. 3x is the greatest common factor of 6x squared and 15x. The greatest common factor in this example is 3x. That's the greatest common factor. But a factor, in general, is just one of the things that you multiply by something else to get a product. So sure, 3x is a factor, but there's another factor here. It's 2x plus 5. Because these are the two things I multiplied together to get this whole product. Within each piece, I have a product of 6 and x squared, so 6 is a factor and x squared is a factor. And remember that 2 and 3 and 1 are also factors, and x squared are both factors of x squared. In this piece, 15 is a factor, and so is x. But so is 1 and 3 and 5. What this piece is called is a term. This is a term, and this is a term. And terms are made up of factors. The terms in this example are 6x squared and 15x. Now that should all be vocabulary you already know, but in some questions in WAMAP, I'm just going to ask you to find the greatest common factor. So your answer would be 3x in this case. But if I ask you to factor out the GCF, that's not just finding the GCF, it's factoring it out. It's rewriting it as the GCF times the other factor. So this would be the answer to find the greatest common factor. Whereas this would be the answer to factor out the GCF, the greatest common factor. See the difference? Here's our next example. I want to factor the greatest common factor from, or factor out the greatest common factor from this polynomial. So I need to figure out what goes into 16x to the fifth, negative 20x to the fourth, and 8x cubed. Well, I can see that 2 goes into all of these. And if I divide the 2 out, if I think of already having pulled out the 2, then that leaves me with only 8 to work with here, negative 10 to work with here, and 4 left here. But 2 goes into all of these as well. So another factor of 2 can be pulled out from each term. That leaves me with 4, 5, and 2. Now, does anything go into 4, 5, and 2? Besides 1? No. So the 2 times 2, 4, is the greatest common factor of the number part of this polynomial. Maybe you could see by looking at 16, 20, and 8 that 4 was going to be your greatest common factor. And for the number part, that's true. But what about the variables? I need to know how many copies of x each of these terms has in common with all the others. This term has 5 copies of x in it. This term only has 4, and this one only has 3. Since what I'm doing by factoring out the GCF is figuring out what I had to multiply by what I had to distribute. What I'm looking for is, what's the biggest thing that might have been sitting out here? What do these all have in common? They all have at least 1 copy of x, and if I take that out, then this one only has 4 copies left. This one only has 3, and this one only has 2. But there's still multiple copies in each one. So let's take another copy out. Taking a copy out here, I get 3, 2 left here, and only 1 left here. But there is at least 1 copy left in each term, so I can pull out yet another copy of x, leaving me with 2 here, 1 here, and none here. No copies of x, so that one's completely gone. Now that I've done that, not only have I found my greatest common factor, but I've also found by undoing this, the thing that I multiplied that greatest common factor by to get my original expression. What that is what's left up here. For the number part of this term, I took 2 out of the 16, which left me with 8, and then I took 2 out of the 8, which left me with only 4. And I took away some copies of x, but I was left with 2 copies of x. In the next term, I took a copy of 2 out of the 20, leaving me with 10, but then I took another copy, and that left me with only 5. For x's, I had 1 x left, so I can write that either as x to the 1 or just as x. In my last term, I took a 2 out of the 8, and then I took another 2 out of the 4, which left me with 2. And I took all of my x's out here, so there are no x's left in this last term. That means this piece can be written as 4x squared minus 5x plus 2. Here's my GCF, my greatest common factor, and here's what's left. How do you check that this is the right answer? Well, I'm claiming that this is the same as the original expression, only in a different form. All I have to do to check it is do the multiplication. Distribute as though you were doing this problem in the other direction. 4x cubed times 4x squared is 16x to the 5th. Remembering that your product property of exponents here says to add exponents when you're multiplying bases. The next term then is 4x cubed times negative 5x. That's going to give me negative 20x to the 4th. Finally, 4x cubed times 2 is 8x cubed. Since this is what I started with, this, with the GCF factored out, looks like this. They're equivalent. They're the same thing written in 2 different forms. This last piece, though, was just me checking my work, checking my answer. The answer I was checking was this here. This is my final answer. This expression, with the GCF factored out, contains the greatest common factor and another factor with what's left over. Here's one more. We want to factor out the greatest common factor. In other words, we want to write it as a product of 2 things, where one of those things is the biggest thing that goes into each of the 3 terms. What number do all 3 terms have in common? What goes into 6, 18, and 12? Well, 2 does, and 3 does, but 6 is the biggest thing that goes into all 3 terms. So that means that I can write part of the greatest common factor as 6. Moving on to the x's, what goes into x cubed, x squared, and x? In other words, how many copies of x does this term, and this term have in common? Only 1. Notice it's the one with the lowest exponent. I have 1 copy of x here, and I have at least 1 copy here, and at least 1 copy here. So I can take 1 copy and write it down as the greatest common factor of x to all 3 terms. Now for the y's. And it's the same thing here, although the term containing the y with the smallest exponent is the first term instead of the last term. I have 1 copy of y in the first term, and I have at least 1 copy in each of the other terms. So now that I've determined what my greatest common factor is, let's rewrite this expression as though we had not yet done the distribution. 6 times x times y times what is 6 times x cubed times y? Well, 6 times 1 gives me 6. X times x squared gives me x cubed, and y times 1 gives me y. I don't need to write the ones because times 1 doesn't change the value. Going on to the next term, 6xy times what is negative 18x squared y squared? One piece at a time, 6 times what is negative 18? 6 times negative 3 is negative 18. X times what is x squared? X times x is x squared. Y times y is what will give me y squared. And the third piece, the third term, same thing. 6 times what is 12? That's 2. X times what is x? Well, 1. And y times what is y cubed? That would be y squared. Again, I don't need to write 2 times 1 when I can just write 2. This is the end of the multiplication that I need to do to get this. So I'll close my parentheses. And now, this looks just like some problems we've done in the past, only backwards. In the past, I've asked you to take this expression and use distribution to get this expression. Today, we're taking this expression and we're using distribution, but we're undoing it to get this expression. What's the greatest common factor of 6x cubed y minus 18x squared y squared plus 12xy cubed? The greatest common factor is 6xy. But the expression rewritten with the greatest common factor out is the whole thing. I want to do one more here. This is a little tricky, and it's not in your book, but it's an idea we're going to see in the next couple of sections. Factor the greatest common factor out of these two terms. It's hard to see what the terms are because the first term is made up of two factors, one of which has two terms in it. But we're looking at the big picture here. This term here, notice that it's separated from the other term by a plus sign. This term here has three factors in it, a 2, an x, and an x plus 1. This term here has two factors in it, a 3 and an x plus 1. What do these two terms have in common? Specifically, what factor do they have in common? That would be the factor x plus 1. It's the thing multiplied by the other things in each term, which is common in each term. In order to get 2x times x plus 1, I could multiply x plus 1 by 2x. And to get 3 times x plus 1, I could multiply x plus 1 by 3. This is actually an intermediate stage in other problems, but you're going to see problems in this form at some stage, so it's worth taking the time now, since we're already talking about greatest common factors, and discussing that the common factors you're looking for don't necessarily have to be just numbers or variables. They can in fact be expressions themselves. Here's an extreme example, and you won't see anything like that this quarter, but it might help make the point. 5t times 3x cubed minus 7x plus 2 minus 4 times 3x cubed minus 7x plus 2. Looks messy, but if all I'm asking you to do is factor out the greatest common factor, I'm asking you to find the factor, the thing that's multiplied by the other things in that term, the factor that's common to both terms. The biggest factor that's common to both terms. Once I've found it, I can undistribute it from the rest of the things in that term. To get this term, I multiplied 5t by this. To get this term, I multiplied -4 by this. So, although this is an extreme case, I've done the same thing here as I did here. I found the greatest common factor, which was not just a letter or a number. Okay, that's enough for this part. There is another video in this section called Factoring by Grouping. One of the things we'll use in that part is this idea here.